Hello, grade 12. In this video, we're going to be speaking about power. So let's start by defining power. Now, what is power? Power is the rate. Remember, rate is divided by time at which work is done or energy is transferred. Right? That is the definition of power. Is the rate, let's just mark this one, is the rate at which work is done or energy is transferred. Okay, now power. If we convert this one into a formula, then power, the symbol for power is P, and power is equal to work done per unit time. Is the rate at which work is done. This is the definition of power. This is a formula to calculate power. Now, work, the unit for work is the joules. This is time. Remember, the unit for time is second, and this is power. Now, power, the unit for power is watt. And the symbol for watt is W. Remember, and be careful, don't you confuse the W for the unit of power with the W for work. Right, this is the definition of power. This is a way to calculate power. However, if we combine formulas, which I'm not going to do right now, later on maybe in other videos we can look at combination of formulas and so on. Power can also be calculating, and this is going to be called average power. Okay, this is going to be called average power. Can also be calculated by the product of the force and the average velocity. Right, this is another way to calculate power. Right, now what is this here stand for? This stands for average velocity. Average speed, velocity. Let's write speed. Average speed, and the average speed, remember, is in meters per second. Okay, this is force, and this is the force is in Newton. Power is the same. Okay, so this is all about power. This is the definition of power. Power is the rate at which work is done or energy is transferred. There is the formula, and then power can also be calculated by the product of force and the average velocity. Okay, so we are going to be looking at one example. We're going to be looking at one example in which we will learn how to apply one of these formulas. Okay, so let's look for the example here. The example, this one. Let's look for this example. Okay. Okay. There is the example, right? Move it here. This one example. So we're going to be looking at this example. Sorry. So the following figure shows an elevator that has a mass of 1,000 kilograms and it carries passengers having a combined mass of 800 kilograms. This is the mass of the passengers. Okay. A constant frictional force of 4,000 Newton retards its motion upward. So the elevator is moving upward, and then the frictional force is in opposite direction of motion, and therefore it is downward. What must be the minimum power delivered by the motor to lift the elevator car at a constant speed of 3 meters per second? So first of all, let's write the data. Let's see what we have here. So we know that the mass of the elevator, I'm going to use E for elevator. Okay, mass of the elevator is going to be equal to 1,000 kilograms. The mass of the passengers, I'm going to write P for passenger, is equal to 800 kilograms. Therefore, this will be mt mass total, and it's equal to 1,800 kilograms. All right, what other data do we have here? We have that the frictional force is equal to 4,000 Newton, and we also have that the speed is constant. And equal to 3 meters per second. All right, this is the data. That is what we have from the question. Let's go on now and draw the free body diagram now. Note, an elevator is moving vertically upwards. So the only axis that is going to be acting there is going to be the y-axis. So now what forces are acting on the elevator? Let's say this is the elevator. Let's see, this is the y-axis. Let's see what forces are acting there. Okay, right. So we have in there tension force, the force from the motor that is pulling upward the elevator, not normal. Remember, this is an elevator. We're not working on the passengers inside the elevator. We are working on the elevator which have passengers inside. So there is not a normal force acting on the elevator. Okay, so this is going to be called tension, or the force from the motor, whatever you want to call it. Okay, all right. So this is the tension force. It could be called the force done by the motor. Okay, what other forces are acting there? Then we have the frictional force pointing down in opposite direction of motion, and there is another force which is going to be the gravitational force, also acting on the elevator. There is not more forces. Okay, tension upward, or the force. Remember, the tension could also be the force from the motor, the gravitational force, and the frictional force. Those are the forces acting on the elevator. Okay, now let's see what formula can we use according to what we have. We have the mass of the object, we have the frictional force, we have the speed, we have three forces acting. So what of the two formulas we have from the definition of work we can use? I think this one will be more useful. We can start trying, and if it's not working, then we'll see what happens. Okay, so let's first of all write down that formula. So yes, let's write down that formula. We have that the power is equal to the force multiplied by average speed. Okay, that is what we have. What force are we talking about? We are talking about that tension. That is the force that we're looking for. And maybe in the data we should write that one. The force T, or the power. Let's write this one. The power done by the force T is question mark. That is what we are looking for. This one here is force T, because we are looking for the power of the force. Okay, so now what is the problem here? We don't have that force. That force is T. Let's probably write P average is equal to T multiplied by V average. However, we don't have that force. Let's use the same color as the free body diagram. We don't have that. We don't know. Now, where is that? That is in the y-axis. So we are going to use one of the Newton's law to calculate that. Now, what Newton's law can we use? Remember, the speed here is constant. If the speed is constant, we have to use Newton's first law. So we are going to say here Newton's first law of motion in the y-axis. All right, and will be useful to say up is going to be positive. That is important. All right, so we're going to be applying Newton's first law in the y-axis. Up is going to be positive. All right, so let's start by writing Newton's first law. Remember, Newton's first law states that the net force is going to be equal to 0. The net force is equal to 0. The system is at equilibrium. That is what Newton's first law states. What forces are there? Tension, which is the one we need, and is pointing upward, so it's going to be a positive, minus frictional force, minus the gravitational force is equal to 0. Those are the forces acting on the y-axis. If we rearrange this formula, tension is going to be equal to gravitational force plus the frictional force. All right. If we start substituting, gravitational force we can substitute the formula is the product of mass and acceleration due to gravity plus frictional force. Now we can substitute all the numbers. I like to substitute the numbers before we go on. All right, so tension is equal to the total mass of the elevator with the passengers is 1,800 multiplied by 9,8 plus the frictional force, which is 400 or 4,000. So let's fix this one here quickly of the data. I'm very sorry about that. It's not 400, it's 4,000. You must be careful when you transfer data from the problem into the symbols. Okay, so it's 4,000 Newton. We go back here plus 4,000. So the tension is going to be equal to, let's go to the calculate this, 1,800 times 9,8, 1,800 times 9,8 plus 4,000, which is the frictional force, and that is going to be equal to 21,640. That is going to be 21,640 Newton. That is the tension force, or the force that the motor exerts on the elevator. Okay, so now this number must be substituted in there, so we can calculate the power delivered by the tension force. So the power, let's go back here, the power is equal, let's say average power is equal to tension force multiplied by average speed. If we substitute, this one is 21,640 multiplied by the average speed, which is 3, is given to us and is equal to 3. If we go to our calculator, we multiply this answer times 3 and we get 64,920. So the answer is 64,920 watt. That is the power delivered by the motor. That is the first example. I want to go to another example. This one is quite easy, okay? But we'll go to another example. Let's just look for the example. So here we are. Let's go to the next page. Let's go for the example. It is this one here. It is that one there. This one. So let's go to this example, and this example is a little bit tricky. So let's be careful with this one. This example says, what is the power required to pump water from a borehole that has a depth of 15 meters at a rate of 20 liters per second? Let's write the data. This question is a little bit tricky. It's coming from the Sijavulo book. I like the book. It's a nice book where they explain step by step how to solve the problem. Okay, so let's first of all write the data. Let's see what we have here. Now, the power that they look in is the power delivered by the motor to pull the water up. I just want to write power of the applied force. Okay, but this could be called by you power of the motor. It does not really matter. Now, what else is here? They're giving us the rate at which the water is being pumped up. All right, so, and they say it's going to be 20 liters per second. That means that they are going to be pumping 20 liters in 1 second. This is 20 liters in 1 second. So the time that we're working with, we want to know how much water is going to be delivered in 1 second. All right, that is the question. So the time is actually going to be 1 second. Right, this is 1 second. Now the height is equal to 15 meters. And now important data that you should know. 1 liter is equivalent to 1 kilograms. So 1 liter of water, or 1 liter, will be equal to 1 kilograms. That means that 20 liters will be equal to 20 kilograms. This is the mass of water that we want to pull up the borehole. They say require to pump this amount of water in 1 second. So they want to pump 20 kilograms of water in 1 second. All right, so this one might clarify now a little bit the question. Okay, so now let's go and write down the formula to calculate power. Okay, power is equal to, remember we have two formulas starting from the beginning. There are two formulas. We are going to select the first one, the definition of power. Okay, it might be easier to use that one in this situation. So power is the rate at which work is done. Okay, but now there is a small problem here. We do not have the work, so we don't know the work. That is a small problem. The time we have it, the time is 1 second. We need to pump 20 kilograms of water in 1 second, so we do have the time. All right, now we don't have this work, but this is the work done by the applied force, which is a non-conservative force. So let's see if we can use the law of conservation of energy to calculate the work done by the applied force, by the motor, by the pump, whatever you want to call it. Okay, so the work done by the non-conservative force, which is the force they're looking for, is equal to the change in kinetic energy plus the change in potential energy. Okay, that is what they want. Let's break down this formula. Okay, this is half mass multiplied by the final speed of the water right at the top, square, minus half mass initial speed of the water square, that is when it's in the borehole. And now before I go on, I'm going to say that the water, while it's in the borehole, does not have any speed, therefore that is equal to 0. Okay, so we're going on. Now we are here, plus the change in potential energy. This is mass multiplied by acceleration due to gravity, final height, minus mass multiplied by acceleration due to gravity, multiplied by initial height. Initial height, when the water is right in the borehole, there is no height, the height is 0, and therefore all this is equal to 0. Okay, now let's go on. We still have here a little bit of things, of tricky things. The mass, we already clarified about the mass. Okay, this is the amount of water we have to get. This is the mass of water. Now, mass of water is going to be 20 kilograms. That one, we know it. It's going to be 20 kilograms. Now, the thing is the speed of the water right at the top of the borehole. Now, how much is that? Okay, remember the speed, the average speed. This is average. I don't know what I was writing. This is average speed is equal to distance traveled. I'm going to write delta x, but this distance is equivalent in this case because it's a straight line motion, all right, multiplied by the time. What is the distance that the water is going to cover? It's going to cover 15 meters, and the time is 1 second. In 1 second, that water must cover 15 meters. So the average velocity or the speed right at the top must be equal to the 15 divided by 1, which is 15 meters per second. All right, that is important. That is going to be substituted in that. Now we are ready to substitute everything in that formula. So let's go back and then substitute that in the formula. Work done by the non-conservative forces is equal to half. The mass is 20. The final speed of the water, is going to be 15 to the power 2 plus, remember that side there is 0, plus the mass, which is 20, multiplied by 9,8, multiplied by the height, which is 15. Okay, and we can do these calculations one by one. So it's 20 multiplied by 15 to the power 2. Just give me a second here. How you say this one? So it's 20 times 15 to the power 2 divided by 2. 2250. Okay, that one will be right here. So the work done by the non-conservative force is equal to 2250 plus is 20 times 9,8 times 15. 20 times 9,8 times 15, and that is 2,940. 2,940, which is equal to 5,000. When you add those two numbers, 5,190 joules. Now we can substitute the work done by the non-conservative force in the formula or the definition of power. So let's do so. Power is equal to work done divided by time is the rate at which work is done. This is equal to 5,190 divided, let's fix that 90 then. It's a 90 divided by 1, which is the time, and that is 5,190 watt. That is the answer for the power delivered for the pump. So this is about power. There are two examples. The second one is a little bit tricky. Next time maybe I'll try to do another example. I hope you understand. Please let me know if there is anything that was not clear and we can look at that. Thank you very much for watching. I hope it helped.